In this video, we're going to talk about sets and Venn diagrams. So we're really going to use sets as a way of discussing a Venn diagram. And the Venn diagram is actually going to allow us finally to look at arguments. So a set is a collection of objects. Let me go ahead and scroll down a bit while I write this. Collection of objects. And the members of a set are specific objects within it. So we use this notation for sets, and you've probably seen it at some point in your math career. It's the little squiggly brackets. So if I say the set of even numbers between 1 and 10 inclusively, meaning you can include 1 and 10 in there, would be 2, 4, 6, 8, 10. See how we put it in the squiggly brackets? In math, when you see squiggly brackets, that means there's talking about a set. Or if you're talking about the letters of the alphabet, you could list them all out, A, B, C, D, and then notice that we use this ... could help us continue the pattern if it's too difficult to list out in its entirety. The set of whole numbers, 0, 1, 2, ... So whole numbers include the number 0, by the way. The ... indicates in this case that it goes on forever. So we need the pattern. I'm not going to list it all out, or continue the pattern. It goes on forever. All right. So that is set notation. So let's look a little bit into sets, and we'll do some set notation here. The vowels of the English language or alphabet, that would be A, E, I, O, and U. But we don't usually classify it as a vowel. The queens of America. Well, America doesn't have queens. So this is, by the way, what they call the empty set. So we can express that two different ways. You could do two squiggly brackets like this facing each other, and it looks empty. That's an empty set. But the more common mathematical way of doing it is using a circle with a diagonal line through it. That is more common to represent the empty set. Okay, so countries that you have visited. Now, of course, this is going to be specific to yourself. For myself, I have visited, and I'm going to not assume, of course, America, since I'm living here. I'm talking about visiting. I have been to Canada and Mexico and England. And that's it. Those are the only countries I've visited. And of course, you can go ahead and list out as many that you qualify for. And it's going to change for each person. Okay, so here's what we're going to really use for sets. What we're really interested in is Venn diagrams. So John Venn created these diagrams as a way of visually looking at information. The first thing you do is draw a rectangle, and that rectangle represents the whole universe, all possibilities. Then we have circles that represent our sets. In this particular case, we're talking about books that are available in hard copies or Kindles. So there's the set of all books that might be outside of that, right? Things that might not be available in either hard book or Kindle, right? I don't know. I'm trying to think of an example. Maybe there's like Google, I think, has some books. So maybe it's Google. All right. So 30, let's just throw a number out here. There could be 30 books that are not being hard copy or Kindle. All right. The 18, those are 18 books that are only available in hard copy. There are 12 books that are available in both Kindle and hard copy. And then there are 15 books that are only available in Kindle. And then this 30 is representing none of them, not in Kindle or hard copy. Whatever universe that looks like. Maybe there's nothing out there. That's a possibility too. Okay, so let's use a Venn diagram to represent some complicated information here. So we have newspaper readers. They read the newspaper. And we're asking which ones they read daily. We're going to consider 3: New York Times, Washington Post, or Wall Street Journal. So as a Venn diagram, go ahead and draw this over here. Draw my big rectangle. I'm going to give myself some space. What I actually have this time are 3 circles with possible overlaps. Regions where they share things in common. People who do read all 3. So this one will represent New York Times. This one's going to represent the Wall Street Journal. And this is going to represent the Washington Post, right? That was the last one. Yeah, Washington Post. All right. So I'm going to fill out this information based on the table. So all 3, that would be this intersection in the middle. And 8 happens to be all 3, right? I'm just seeing that right here. All 3, 8. So that's going to be the middle, the intersection of all 3 of the circles. Another easy one to do would be this last category where it's none. That's going to be 15. That's going to be out here in the universe where they don't read those particular 3. All right. So the fact that they use the word only actually makes our life easy. They're qualifying that these are people who only read the New York Times, and they have to say that. They have to say only in order for that to be true. Otherwise, we have to do some different assumptions. So 24 people who read the New York Times, 27, the Wall Street Journal only, and 26 for the Washington Post. Okay, so these next 3 are going to be represented in these 3 overlaps that don't include all 3, but only 2 of them. So let me try to carefully erase that. There we go. So people who read New York Times and Wall Street Journal only, there are 14. That's good. It doesn't over the Washington Post circle. Okay. Then we'd have 16 for New York Times and Washington Post, and 13 for Washington Post and Wall Street Journal. So there we go. That's how we'd fill this out. So let's answer some questions about this. How many people surveyed read the New York Times? So I see that there's actually quite a few people. And there's not just 24. There are people who read the New York Times who just happen to also read other newspapers. So I have to include all of that information. So in other words, it's going to be 24 plus 14 plus 8 plus 16. So all of those people read the New York Times. If you grab your calculator and total that up, I happen to get 62. All right, how many people read at least one of the newspapers? Well, I happen to know that this first circle is 62. And if I add in 27, 13, and 26, those are the other numbers not included. 27, 13, 26, for a total of 128. That's how many people read these 3 newspapers, just period, one of them, at least one of them. Okay, so what percent read the Wall Street Journal? So first of all, I need the total, which is pretty easy to calculate now because I've told everything but the 15 who don't read these 3 newspapers. So if I add 15 to that, is 143. So that's the total number of newspapers. All right. So read Wall Street Journal. Okay, so here, let me come back up here. Oops. So 14, 27, 8, and 13. That's what I want to add. 18. So that totals up to, I got 62 again. Interesting. Now I'm questioning myself. 49. Yep, that's right. Okay. So if I take my calculator and divide 62 by 143, I come up with 0.43 as a decimal, which would be 43%. Okay. So there you go. allows me to kind of answer some fun questions. More terminology. So I mentioned this phrase in here, overlapping sets. Okay, that means they have members in common. If the set has no members in common, they're called disjoint. So they don't have anything in common, they're disjoint, and we draw that differently. And then we also have the idea that something might be a subset of something else. That means that all the members of A happen to also be members of B. So we have different ways of drawing subsets versus disjoint. So disjoint, wow, that's sad S, looks like this. Since they have nothing in common, here's my universe. I'll have A as this set and then B as a separate set, and they don't overlap. So I'm not going to bother if they're disjoint. Subset means that everything in one set is also in the other. So if A is a subset of B, here's B, and then A is actually inside of B. Everything that's in A is also in B. So it's within the subset. Okay, so let's look at this. State an example of two sets that would be considered disjoint and draw the Venn diagram for this case. So let's come up with a disjoint example. So for me, I'm going to use a really nice, obvious one, age. So let's say age, A is representing 20-year-olds. And B represents 30-year-olds. So that's two examples of two disjoint sets. There's no way somebody can be in both A and B. So this would be how I draw this. All right. This would be, by the way, an exclusive case of or an example of an exclusive case you could use. All right, let's do two. So let's still use the same A. Let's say A is 20-year-olds. But this time, let's say B is a female or females. In this case, we have some overlapping. There are 20-year-old females. There are also females that are not 20-year-olds. And there are also 20-year-olds that are not females. So we have that kind of classification where they have some overlap. It's not a small overlap, but it's still just some. Okay, let's do a subset. Now this time I'm going to have to change it. And I'm going to correct the wrong I said earlier. Let's let A be dogs. And B be mammals. So in this case, dogs would be subset of mammals because dogs are a type of mammal. So propositions that claim a particular relationship between two categories are called categorical propositions. Of the two sets, one set appears the subject of the sentence, and the other one is what we'll call the predicate. For example, in the proposition all whales are mammals, whales are the subject, mammals is the predicate. So we're going to look at this, or propositions, just so we can kind of understand. It's usually easiest to identify the subject. All whales are mammals. Well, we already know that whales are the subject. Mammals are the predicate. No fish are mammals. Fish should be the subject. Again, mammals, the predicate. Some doctors are women. Doctors would be the subject. The predicate in this case is women. Still, teachers are subject, even though there's a not, who cares? Men are still the predicate. So for the given categorical propositions, do the following. Rephrase it so that it's in the right form if necessary, okay? We're gonna look at which one's the subject and which one's the predicate, and then we're gonna draw a Venn diagram of it. Okay, so in this case, and I'm gonna use S and P for subject and predicate, okay, for ease. All salty foods cause high blood pressure. So in this case, the subject is salty foods. The predicate is high blood pressure. Technically, I should probably say cause high blood pressure, but that's okay. Okay, so in this case, if I were to draw a Venn diagram for this, if we're saying all salty foods cause high blood pressure, that's a subset, because what we say is that we have this category of high blood pressure and salty foods are here within it. They all cause high blood pressure. That's how we've stated this. So this would be an example of a subset Venn diagram. Gave me a subset Venn diagram. No swimmers are afraid of water. So in this case, S would be swimmers. The subject is swimmers. The predicate is afraid of water. So if we're saying that no swimmers are ever afraid of water, if this is P, then S is disjoint from it. They would be disjoint sets. So a no statement like this would give us a disjoint set Venn diagram. Some movie stars are redheads. So in this case, S would be movie stars. P are redheads. Oops, that's not how you spell redheads. So this would allow for possible overlap. So I want to draw it with overlapping sets. So here's S, here's P. So we have movie stars and we have redheads. And there are definitely redheads who are not movie stars, and definitely movie stars are not redheads, but there are some that are. So we're allowing for that possibility. So this is going to kind of help us when we're looking at arguments. When there are no statements, that means that we have this disjoint version, or all statements give us this subset version, and that's really useful to us. Okay. So let's look at a final example that kind of ties together everything we just talked about. We want to create a two-way table for this example. In a trial of new allergy medicine, 120 people were given the medicine. 80 were given placebo. Of those given the medicine, 90 showed improvement in their allergies. Of those given the placebo, 20 did not show improvement. So I'm going to make a table of this information. Hopefully I made this big enough. So 3 columns, 3 rows. And what I have is that people got medicine or the placebo, and they either improved or didn't improve. So I'll say not improved. I'm gonna cough, sorry. Okay, so we happen to know that 120 people total were given the medicine, and that of those given the medicine, 90 showed improvement. So this is 90, and that leaves 30 left over to be not improved, because this totals up to 120. And we saw this before, okay? So for the placebo, 20 didn't show improvement, so this would be 20. And since this is a total of 80, that leaves 60 who did improve. All right, so let's make a Venn diagram of this information. I'm going to zoom out a smidge just so I can see the table when I make this. So when we do this Venn diagram, we have to decide sets. And typically, you need to make one set from one of these two and one set from one of these two. So we kind of want to decide which two pieces of information are probably most important to us. So in this example, if we're talking about a study with a medicine, we're interested in the people who took the medicine and whether or not they improved. So I'm going to make that my two sets. I'm going to let set A be, or one set be the medicine, and the other set be the improvement. So medicine and wow, terrible circle. I probably should make the bigger box, the universe box, a little bit bigger. There we go. And this will be the improved category. So those are the two pieces of information we're most interested in. Okay, so we have people who fall into both medicine, into the lap between those. We have people who improved but didn't take the medicine. Those are the placebo people, and there were 60 of them. We had people who took the medicine but didn't improve. Those would be these 30 people. And it didn't improve, they took the placebo. Those are those 20. So that's how I draw that in a Venn diagram. So how many people received medicine, didn't improve? We already know that, there's 30. How many people who received the placebo improved? Well, we happen to know that too, that's 60. And we calculated those when we created our table.